Okay, so we're going to continue looking at examples of just taking parameterizations or vector-valued functions that take real inputs and output vectors. Our next example is x equals cosine t, y equals sine t, z equals 2 minus sine t. And so the strategy that's worked for us so far, is to look at a top-down view, to look at something maybe that gives us a sense for what the heights are, and then maybe we'll wrap that up into a 3D graph. Actually, this time let's plot some points too. Let's just think about points and what that might mean for our curve. So top down, again, I'm looking at just in the xy plane, like what is the shadow of this thing if I'm looking from top down. And again, notice that we have this property that x squared plus y squared equals 1. So all of my points on this curve will live on the cylinder. They're all on the cylinder. And so the shadow is going to be something like this, maybe. It's a circle. In terms of heights, things get a little bit more complicated, but let's try to work through this. If I think about z in terms of t, what's happening? Right, so 2 minus sine t, that's a vertical flip of the sine t function shifted up by 2. Okay, so I'll start here at the point 0, 2. And remember, the sine function looks something like this. This is the negative sine function, right? And so we have some nice points here at pi over 2 and 3 pi over 2. This is reaching its maximums so we have the points, for example, pi over 2 for t and 1 for z. We have 3 pi over 2 and 3 for z. And then at each of these points, we have pi, comma 0, and 2 pi, comma 0. So let's think about some of the points that live on this thing in total. Right? So we have t, and let's look at what the point x, y, z should be in that case. So it's always going to live on the cylinder. Remember, it's always going to be that x squared plus y squared equals 1. So let's look at the points t equals 0, pi over 2, pi, 3 pi over 2, and 2 pi. Because those are friendly values I know for cosine and sine. Right, so when I plug 0 into cosine and sine, I get 1, 0. And then when I plug it into z, I get 2. Then I have the point 0, 1, 1. Then for pi, I have the point -1, 0, 2 again. 3 pi over 2, I have 0, -1, 3. And then for 2 pi, I'm back to 1, 0, 2. So it does actually complete an entire period in 2 pi. So that's all I really need. And then I would, of course, have to fill in the gaps between those two. If you use GeoGebra, you can graph this thing very easily. If you want to do this by hand, this is very, very difficult. Certainly something that might have taken me several cuts to make. Let's see if I can do it. Okay, so start with a z-axis. Although it may not be obvious, I'm going to cheat and make my y-axis in this direction and have x coming out this way. It's not at all obvious why this is a good idea. It's just because I've seen the graph before. Okay, so 1, 0, 2. 1, 0, 2 is going to be 1, 0 in the y direction and 2 up. 0, 1, 1 will be 0 in the x direction, 1 in the y direction, and 1 up. -1, 0, 2 will be -1 in the x direction, 0 in the y direction, and 2 up again. And finally, 0, -1, 3, that'll be 0 in the x direction, -1 in the y direction, and 3 in the z direction. And so if you fill in all the points between, actually, you get something that looks something like that. Really poorly drawn. I encourage you to look this up on GeoGebra and show that it doesn't really look like this. If you make the line fat enough, it might work. It's a poorly drawn tilted circle. Okay, we actually will revisit this example and show that it's a tilted circle. But anyway, kind of cool.